So hey guys, now we're going to learn about the properties of fluids in fluid mechanics. So this is also another important, very basic introduction. So please, if you want to follow through fluid mechanics, I am asking you to at least have a glimpse of the terms, definitions, the various properties of fluids that you're going to do into details. This entire course and all this entire channel is meant for beginners. So if you're an intermediate, there are other channels outside there for you. But as of now, it's time to have a glimpse. Now, there are several properties of fluid. First one is density or mass density of a fluid. There's also the weight density of a fluid. There's the specific volume of a fluid. There's a viscosity of a fluid and other viscosity factors that we'll discuss later. So number one, the density or mass density of a fluid. So it is defined as a ratio of mass of a fluid to its volume. It is denoted by the symbol rho, and its SI unit is in kilogram per cubic meter. For liquids, their densities may be considered as constant. However, densities of gases change with variations of pressure and temperature. So density of a fluid is equal to the mass of a fluid all over the fluid volume. It is important to remember that the density of water is 1 gram per cubic centimeters or 1000 kilogram per cubic meter. So the second one, or the second property of fluids, is the weight density of fluid. It can also be called the specific weight of fluids and is the ratio between the weight of a fluid to its volume. It is denoted by the letter W. W is the fluid weight all over the volume of the fluid. So weight density being fluid weight over the volume of fluid, which is equals to the mass of the fluid times the acceleration due to gravity over all over the volume of fluid, which is also can be simplified to the fluid mass times gravity all over the fluid volume, which is density times gravity. So weight density is equals to density times gravity. In short, the mass per unit volume of fluid is density, and to get weight you must multiply by gravity. The specific weight of water then is 9.81 times 1000 Newton per meter cubic. Number 3, the specific volume of a fluid. It is defined by the volume of a fluid occupied by a unit mass. Specific volume of a fluid is the volume of a fluid occupied by a unit mass. A specific volume is equal to the volume of the fluid all over mass of the fluid, which is also equals to 1 over the mass of the fluid all over the volume of the fluid. So a specific volume is so expressed as cubic meter per kilogram and commonly applies to gases. Specific gravity is another property, and specific gravity is defined as the ratio of weight density or the density of a fluid to the weight of the density to the weight density or the density of the standard fluid. For gases, specific gravity is equal to weight density of that gas all over the weight density of air. So for gases, specific gravity is equal to the weight density of that particular gas all over the weight density of air. For liquids, specific gravity is equal to the weight density of that particular liquid you are handling all over the weight density of water. We can therefore say that weight density of a liquid is equal to the specific. We can therefore say that weight density of a liquid is equal to the specific gravity, which is the weight density of that liquid over the density of water. Weight density of water times 1000 times 9.81 Newton per meter cubic. That is gravity. Density of water is equal to the specific gravity times density of water. So that is specific gravity times 1000 kilogram per meter cubic. So another property of a fluid is viscosity, and this is a property of a fluid that offers resistance to the movement of one layer of a fluid over the other adjacent layer. Consider two layers of a fluid, distance dy apart, moving one over the other at different velocities, e.g. u and u plus du. I've drawn a simple diagram of two liquids that are moving in the same direction, one adjacent over the other. So this one have traveled a distance u and the other one has traveled a distance u plus du. So the viscosity together with the relative velocity causes shear stress acting between the two fluid layers. So in between here is shear stress. So we can also describe that in a graphical representation. We have the y-axis and the x-axis that is represented by u. So we are shown dy and du, change in y all over change in u. So these are the distances u plus du. So and this line depicted by the diagram here is called the velocity profile. So the graph above shows the velocity variations near a solid boundary. So those are the variations near a solid boundary. The top layer hence consists a shear stress on the adjacent lower layer. So lower layer does the same to the adjacent top layer. This shear stress is proportional to the rate of change of velocity. This shear stress is proportional to the rate of change of velocity with respect to y. So it is denoted by the letter tau, and tau is equals to du all over dy. That is, tau is directly proportional to d over dy. We're going to add constant mu, where we're going to get tau, which is the shear stress, is mu du all over dy, where mu is a constant proportionality and is known as the coefficient of dynamic viscosity. Du all over dy is the rate of shear strain or the rate of shear deformation or velocity gradient. So mu is equals to tau all over du over dy. Thanks.